objects. Okay. So we're not.
Excuse me, does this conclude the chapter 8 stuff?
Basically, we're basically coming to an end, but this last part is a bit challenging for some students to wrap their head around. So I'm going to spend today and Monday on that. Okay. All right. So let's continue here with our notes. So I'm just going to give you first. I'm going to talk about a shortcut here. Often you will be asked to determine the dimensions of the diagram or new object if so, use the shortcut. The following formulas. Okay, so all these formulas are derived from the original here, which is that a scale factor is always a diagram over actual, or you can also think of the scale factor as new over original. That's when you're making a copy of something, a replica, okay? So we can always say that to find the diagram, right, the dimensions of the diagram, we can just say diagram is equal to k times actual. Like if you think of cross multiplying and dividing, right? If you want it, if this is your unknown here for the diagram, you would cross multiply and divide, and the dividing is really just 1 here. So it's to find the dimensions of the diagram, you just go scale factor times the actual dimension. Or when you're looking at this form, this version of the formula for the scale factor, you would just say the new dimension is going to be k times the original. Okay, so these are the new ones that I want you to have on your study sheet because it makes things a lot faster. Okay. So example, a rectangular cake with dimensions of 24 inches by 36 inches will be enlarged by a factor of 2.5. Calculate the dimensions of the new cake. So they'll make a copy of it, they make a bigger version of it, And so how would you come up with the dimensions of that new cake? Okay, so first of all, you need to know that the dimensions that they are giving you correspond with what we call the original, right? That's what you start off with. And so I'm going to use original and new in this case instead of diagram and actual, because you're making a copy of that cake. So it's cake and cake, right? It's not picture of the cake or diagram of the cake and the actual cake. Like, it's not that scenario. So I'd rather use new and original. So the new one will be obviously bigger. So we're not going to draw it to scale, although we could. And so this is the new one. So this would be your length technically, and this would be your width, right? And so how would you come up with the dimensions here? So this is how you would do that. The length of the new shape would be the scale factor, right, times the length of the original. And what's the length of the original? It's 36 inches. So that's 2.5 times 36. That's 90 inches. And the width of the new would also be found by just multiplying the scale factor times the original width. Right? So you just go like 2.5 times 24, which is 60 inches. So here you have your new dimensions. Okay, so the 90 would go here, and the 60-inch would go there. And by the way, if you've done your homework, you will have noticed that when they asked you to make a scale diagram of something, the answer key labeled the sides of that scale diagram using the measured length, right? But in reality, you're supposed to, if you make a scale diagram, you always put the actual measurements on the along the side. So there, it's a little bit of a discrepancy there. And so just so you know, it's not like I didn't know what I was talking about. It's just they do it differently there, I guess, so you know how long they should be when you measure it. Okay. So what have I done here? I've given you a shortcut to quickly come up with the dimensions of the new shape that we're talking about, right? So now we're going to go into the 2 dimensions and 3 dimension. We're going to be talking about area and volume, and how does the scale factor affect that. Okay, so I will say here, when working with one-dimensional values, and I'll put down in brackets such as length, width, radius, height. Those are all one-dimensional values, right? Then it's always just going to be the K, the way you've seen it so far. Okay. When working with one-dimensional values, comma, enlarging or reducing will affect only by a factor of K. Okay, so those shapes will only be affected by a factor of K. Right. This changes when working with two-dimensional values, that would be area or surface area. And how will you know that it's area or surface area? Sorry, right? You're looking for centimeters squared or square yards, etc. Okay, so it changes when working with two-dimensional values or three-dimensional values, and that'd be volume, capacity, and you will know that by going centimeters cubed or cube yards or cubic feet, etc. Okay, so it changes. Like you're not just when you're going from a one-dimensional to another one-dimensional, if you're changing it, enlarging it, or reducing it, like let's say here, if you're going from 36 and you're increasing it by 2.5, then you get your 90, right? So everything is just affected by the scale factor as is, okay? But this changes when we're working with areas and with volumes, okay? So here we go. I will go to my back side here, and we'll write this down. Sorry, I didn't mean to write that down. A rectangle has dimensions of 20 feet by 15 feet. A new version will be made using a factor of 3. Let's explore their areas, their corresponding areas. So let's talk about the original here. And we know that it's 20 feet and it's 15 feet here. And we will have the new one. And we know that it's enlarged, I hope, because k is the scale factor, k is bigger than 1. So we know that it's a bigger version of the original. This is the new one. Okay. So what we know is that k is 3. So essentially you're taking that, you're increasing it by a factor of 3, and you get the new one there. Right? So k, the scale factor is 3. That's an enlargement. Let's come up with these dimensions here. So the length of the new one will be 3 times the length of the original, and the same units are applied. So that'd be 60 feet. So you put down 60 feet here. Okay. The width of the new is going to be 3 times the width of the original, and that's 45 feet. So we know that this is 45 feet here. So that's 60 by 45. So we have now both shapes, the original and the new. We've converted each dimension and it has been affected by a factor of k. So I will just reiterate, there's the scale factor of 3 and it appears here and it appears here as well. Okay, so it's everywhere. Let's talk about the areas now. Let's figure out the areas, and it's fairly simple. We're talking rectangles, right? So the area of the original, and we have to distinguish, right? That's why I put in subscript, I put original, would be 20 times 15. And so the area of the original would be 300, right? 300 square feet. Let's talk about the area of the new shape that we've just created, right? That'd be 60 times 45. And that is 2,700 square feet. I want you to pay close attention. So I'm gonna let you write it down first, okay? Give you a few seconds there. I'm gonna just talk in the meantime while you're writing this down. I don't know, you don't need to be a math wizard or a math genius, right, to observe something particular here. We know that, right, let's just look at the 20 here. To go from the length of the original to the length of the new shape, we can clearly see that it is 3 times bigger, right? If you compare these two sides, it's fairly easy to see it's 3 times bigger. If you're looking at the widths, it's also fairly easy to see it's 3 times bigger, the new one compared to the original. When you're looking at the areas, do you think that the new is 3 times bigger than the original? And the answer is no, right? Like the area of the new one is much bigger than 3 times the original. Let's figure out how many times bigger our new one is compared to the original. So what we will do here is area of new divided by the area of the original, okay? It would give us 2,700 square feet divided by 300 square feet. And what would you get there? 27 divided by 3, what do you get? 9, right? Because you can cancel the zeros. You cancel the square feet as well. 27 divided by 3 is 9. So what we conclude from this is that area of new is 9 times larger than the original. 9 times larger than the original. And I'm going to add something to the notes now. How can you get from 3 to 9? What happened? Right? Because we were 3 times, everything was 3 times bigger. All of a sudden, the areas are not 3 times larger, right? It's not a factor of 3, it's a factor of 9. And this is where I need you to pay close attention. How do you get 9 from 3? You square it. And so that really means that we took the scale factor and we squared it. Okay, so I'm going to highlight the 3 here. Okay. So another point here, the areas, sorry, the area of the new rectangle has been affected by a factor of k squared. Okay. So here's this is going to be our conclusion after all of this. We know that k squared, right? We got a 9 when we did the following, when we went area of new divided by area of the original. Or, that's stated in the other terms, we can also think of, remember new, we can also use diagram over area of actual. They're the exact same thing. These are new. How do you know it's going to be k squared? When we're talking areas. Okay, when we're talking areas, notice the k squared. It's a squared there. Okay, that's the new part about these two formulas here. All right. So the beauty is here, I mean, I don't know, you might not see the beauty in it, but really I wouldn't have had to give you any dimensions. I could have just said, hey, the area of the original is 300 square feet. If a rectangle has been created, a new one, and it has been enlarged or reduced, it doesn't matter, by a factor of, let's say, 1.5, how could you come up with the area of the new shape? Well, it's going to have been affected by a factor of not 1.5, but by a factor of 1.5 squared. Okay, so when you're talking areas, everything is affected by the scale factor squared. So from here, I will derive this. Okay, that the area of the new shape would have to be, could be found by going k squared times the area of the original shape. Or in this case, the area of the diagram could be derived by going area of actual. Sorry, I wanted the k square in there. First, I want to be consistent. K squared times area of actual. These are also, I would put these formulas down, all these close together, and notice that this is with two-dimensional, right? We're talking areas, so centimeters squared, meters squared, squared yards. Like whenever you see a number associated with squared units, you're gonna have to be very careful to include that square there. Okay. So that is for squared. Now we're gonna do, and just quite frankly, watch this, right? Like all your units are squared, and all of a sudden, right, k squared, right? So it's areas, squared units, k to the power of 2. So you can kind of predict what it's going to be for volume, right? So I will add one more formula under these. Okay. If you wanted to know what the scale factor is of, if I gave you both areas of the new and of the original, to determine the scale factors, if both areas provided, both areas given, we go k is the square root of, right? Because you would have both of these, so you'd have to square root both sides. Area of new divided by area of original. or K is square root of area of diagram divided by area of actual. And right now, you're just gonna have to take my word for it, and I will show you when to use which, okay? They each have their specific function, and this is all two-dimensional, okay? And because 3D works the same way, I will go into the three-dimensional component as well and talk about that, okay? So I know your head might be spinning right now, but hang in there, and you're gonna have to do some questions and practice this more than ever, because this is new, right? You haven't talked about this before. So now we're gonna talk 3D, okay? Volume capacity, okay? That is like how much can you fit into a shape, right? Volume is how much space does that occupy. That's usually for solids. Capacity is for like hollow 3D shapes, right? So let's talk about it. A box measures 2 inches by 3 inches by 5 inches. If a new one will be made using a factor, it's the same thing as scale factor, by the way, of 1/2, okay? Determine the dimensions of the new box. Okay? So to draw a box, what I do is, and everybody, you probably will do a much better job than me. But I just start with a parallelogram like that, and then I just go up by the same amount so that you can copy the parallelogram in the bottom. You always want to have parallel lines, right? So try your best to make a box like that. And it doesn't matter where you put them really. 2 inches, 3 inches, 5 inches. And this is the original. Okay. And the new one, is the new one going to be bigger or smaller? The new one, it's a factor of 1/2. That's less than 1. It's going to be a reduction. So I don't know if you want to make a note of that here. K is less than 1. It's a reduction. So it's going to be a smaller box that you're making. So make sure that it looks a little smaller, right? Doesn't have to be perfect. Okay, there's my new box, and I need to know the dimensions of each one of those. So I don't know where you want to do the math, but I know that to go from the original, I will have used a factor of 0.5 to get to the new. Okay, so length of new will be 0.5 times, what's the length of the original? It's 2. The width of the new shape will be 0.5 times 3. And the height of the new, we have 3 dimensions now, right? And so it's 0.5 times 5. So we get 1 here, we get 1.5 here, and we get 2.5 there. It's all inches, right? It's a little bit close to my new shape, but that's fine. So we got 1 inch, we get 1.5 inches here, and we get 2.5 inches there. And I like to have that visual there, right? You didn't really have to, but I think it makes it easier to see where we're going and to follow. Okay, so you've got your length of the new, and notice that all of them have been affected by a scale factor of k. Right? They've all been, so scale factor was 0.5, so the length is affected by 0.5, the width, the height, those are all one-dimensional. These are all one-dimensional values, right? They just measure length. And so now, let's come up with the volume of the original. And you know that the volume of the original is 2 times 3 times 5, right? It's the area of the base times the height. That's the definition of volume, by the way, right? So volume of original, we can do this in our heads, right? 2 times 3 is 6. 6 times 5 is 30. 30 cubic inches. The volume of the new shape, of the new object, is 1 times 1.5 times 2.5. Volume of new is, and this one, just to make sure, I will do that on my calculator as well. That'd be 3.75 cubic inches. Now, again, it's fairly easy to see when you're looking at the linear dimensions, the one dimension values, that, right, 2 goes to 1. Yeah, I can see that it was reduced by half, right? And if you look at all the other sides, they've always been affected by a factor of k. However, you can see, right, that the volume is not half, right? It is definitely not half when you compare the new and the original. So what we do is we will go volume of new divided by volume of original. And what is that going to be? Well, we go 3.75 inches cubed divided by 30 inches cubed, and the units just go. And let's see what we get there. What is it that we get there? And in this particular case, I will make a little change here to our strategy. Actually, what happened there? Yeah, I'm just gonna massage this a little bit so that you see exactly what happens here. Let's divide both of them by 3.75, which is the smallest value in that fraction. Okay, and what does that give us? We get 1 for the top. And if we go 30 divided by 3.75, what do we get? You should get 8. Okay? And let's talk about the original scale factor. The original scale factor was half. Okay? Notice there 0.5 and it's half. So how do you get 8 out from 2, which the original denominator was 2? How do you get 8? Well, if you think about it, 2 times 2 times 2, right? 2 to the power of 3 is 8. So really, this can be rewritten as 1 over 2 to the power of 3. Oh no, this goes back to IPR. I don't want to hear about this, right? No, it's the power is just affecting the top and the bottom, which is really k, that scale factor that we started with, to the power of 3, because we want to generalize. We want to say like, oh, okay, so in general, the volumes will be affected by a factor of k cubed. Okay? So let's add our notes here. Volume of nu has been reduced by, and here you can say it has been reduced by a factor of 8 because you're talking reduction, by a factor of 8. And volumes will be affected by a factor of k cubed always. Okay. And so to conclude, k cubed is going to be volume of nu divided by volume of original. Or you can think of it this way, k cubed is volume of diagram, volume of actual. And remember, they're exactly the same. Nothing changes. It's just sometimes it's easier to think of something as diagram and actual, and sometimes it's easier to think of something as new and original. And so from this formula, we derive that if you wanted to know the volume of the nu, you could just go k cubed and multiply it by volume of original. And I'll put this in brackets, that's better. Or volume of diagram is going to be k cubed times volume of actual. And last but not least, I'm trying to be consistent with the two-dimensional, right? If you wanted to know k and you're talking and you were given both volumes, watch this carefully, listen carefully. It's cube root of volume of nu divided by volume of original. Or k is cube root volume of diagram over volume of actual. Okay, so there we have that, and I would like to do at least one example. An example of it before I send you off. So I'll make sure you've written this down. All right, let's do some examples here. Examples. Jasmine is making a kite using a scale diagram that has a scale of 2 to 25. The area of the fabric on the diagram is 20 centimeters squared. Calculate the actual area needed to build the kite. Okay, so couple of things to note. You're working with areas. So that's 2D, right? So you're gonna have to refer to area of, in this case, it's probably better to use diagram, area of actual, right? So this is where you would want to go. Emphasis on the k squared, okay? What are they giving you? Out of the 3 components, you need at least 2, right? So let's do a checklist here. What's the scale factor? Do you know the scale factor? Don't worry about the power just now. We'll do that later. The scale factor is 2 to 25. And there are no units in there, so you can just turn that into a fraction, like so. Okay? And out of the 2 areas, they give you the area of the diagram. Area of diagram is 20 centimeters squared. So we can go ahead and substitute that in. Okay? Sub in. So we have 2 over 25. We have to square that because that's what it says, right? Because the areas are related by a factor of k squared, not just k like linear dimensions would be. Then you have the area of the diagram, which is 20 centimeters squared, and area of actual, we don't know what it is. Down the road, I might make that x, right? So we don't have that much to write. And here you have to be, I want you to just apply that power to both numbers that appear here. So 2 squared would be 4. 25 squared, use your calculator, right? 25 x 2, that's 625. And this is 20 centimeters squared over area of actual. So without knowing any of the actual dimensions of that kite, we can figure out like what the area would be of the actual, like how much fabric do you need in real life. So you go cross multiply and divide. Area of actual is 20 times 625 divided by 4. Area of actual would be 3125. And what are we in? What units were we in? We were in centimeters squared. So there you have it. Okay. I'm going to make a B out of this here. B. If Jasmine made another kite with an actual area of, let me just 500 centimeters squared, let's say. If Jasmine made another kite with an actual area of 25 centimeters squared, determine the scale factor used. So now we assume that we don't know the scale factor, but we're still working with areas, right? So we would still start with this one, right? Area of diagram, area of actual. Okay. What is it that we want to know? We want to know what K is. Scale factor means I want to know what K is, not K squared. Okay, we're almost done, guys. And so we go K squared is equal to, what's the area of the diagram? It was 20 centimeters squared. We knew that from the top, right? And what's the area of the actual kite that she made, right? She made another kite and she figured, hey, that one was 500 centimeters squared. Okay, so this goes in here, and we knew that that was 20 from the beginning. So what do you do now? Well, first of all, cancel out the centimeters squared. That's perfect, right? That's what you want. And you can also cancel out zeros here. So K squared would be 2 over 50 essentially. What do you need to do at this point? Remember I told you to take the square root. I gave you a formula like that. So you don't need the formula. You can just slowly derive it and just know that you need to take the square root. But K is essentially the square root of 2 over 50. Okay, so let's find out what that is. And I'll show you how to type that in. Okay, I would say you go second x2 brackets 2 divided by 50. By the way, you didn't need to reduce, right? You could have gone 20 divided by 500, right? It would have given you the same result. And then that's 0.2. 0.2, and it's okay to state your scale factor as a decimal. There's nothing wrong with it. Okay, so that's what happened there. You came up with a scale factor of 0.2. And does this make sense? Yes, because remember, this is always telling you what happened to the original or what happened to the actual, right? This is a reduction of the actual. So the diagram obviously is a reduction of the actual. And that's what needs to be said, right? From 500 to 20, obviously that is a reduction. So you expected that. The key here is the square root. Okay, homework. I won't give you a whole lot. Okay, I will tell you to go to page 509. Right, and you're just gonna do 3, which you have to watch out with the units there. We might talk about that. 3, 4, and 6, and 8. If you struggle a little bit, that's fine. You need to try it, okay? Using my notes, using the formulas that I've given you, okay? And then check the answers at the back.